All right, so this video is part 4 of Unit 3, and this is the last video of the course. We are looking at sequences and series here, and we're going to start out just talking about some basic introductions of some terms and some specific notation. So the first thing we're going to look at is what a sequence is, and a sequence is just a list of numbers that follows a certain pattern. We can have infinite sequences or finite sequences. An infinite sequence does not end, it has no last term. A finite one ends and has a last term. This one does not go on forever, this one does go on forever. Now, sometime in your math history, hopefully you learned what a factorial is, if you see this term here with the exclamation point in it, and that is a factorial where you're multiplying all of the numbers less than that. So for example, if you have 5 factorial, what that means is 5 times 4 times 3 times 2 times 1. If you had 7 factorial, that would be 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, 1 factorial is equal to just 1, and 0 factorial by definition needs to equal 1 as well. So this is kind of counterintuitive here. You'd think 0 factorial would equal 0, but it doesn't. It equals 1. Now we're going to look at a couple of different types of formulas here, and the first one is called a recursion formula. It has an a sub n minus 1 in it, meaning it's going to need the previous term to find the next one. The other type of formula we will see in this last part of our Unit 3 is called an explicit formula, and that's a little bit different. So we're going to look at some examples here and just practicing finding the first few terms of a sequence. So here, the equation we're working with is a sub n is equal to negative 1/3 to the nth power. And it wants us to find the first 4 terms. So a sub 1, the first term, a sub 2, the second term, a sub 3, the third term, and a sub 4, the fourth term. And all we're doing is plugging in 1 for n, plugging in 2 for n, and this is what's called an explicit formula. So negative 1/3 to the first power is negative 1/3. Negative 1/3 squared is 1/9. Negative 1/3 to the third power is negative 1/27. And negative 1/3 to the fourth power is 1/81. The next formula is what's called a recursive formula or a recursion formula, where we need the term before it. So if I want to find a sub 1, a sub 2, a sub 3, a sub 4, the first 4 terms. Well, a1 was given, so a1 is 2. And if I want to find a sub 2, well, a sub 2, our n value being 2 then, if we have 2 minus 1, that would be 1. A sub 1 is equal to 2, so that would be 5 times 2, and that's 10. Then for a sub 3, 3 minus 1 would be 2. I need a sub 2 multiplied here, so 5 times a sub 2 is 10, so that would be 50. And then for a sub 4, if I want to find a sub 4, n is 4, 4 minus 1 is 3, I need the term before it, so a sub 3 was 50, so 5 times 50 is 250. And that's the first 4 terms. And then the next one, we can see that we have a factorial in this equation here. So if I want to find the first term, the second term, the third term, and the fourth term, plugging in 1 minus 1 is 0. And like we just talked about, 0 factorial is 1. So negative 2 times 1 is negative 2. Excuse me. For a sub 2, n is 2. 2 minus 1 is 1. 1 factorial is also 1 times negative 2 is negative 2. 3 minus 1 is 2. 2 factorial, well, that's 2 times 1, be negative 4. And then 4 minus 1 is 3. 3 factorial is 3 times 2 times 1. That's 6 times negative 2 is negative 12. So that's the first 4 terms there. And then this next example is not evaluating a sequence, but it's evaluating an expression with a lot of factorials. And you can type a factorial into a calculator. However, It usually gives us really, really large numbers that sometimes your calculator cannot calculate. So it's often helpful to evaluate these by hand a little bit first and then type in your calculator. Now 20 factorial, that is really long. That's 20 all the way down to 1. But on the bottom I see 18 factorial. So rather than writing out 20 factorial, I'm going to write 20 times 19 times 18 factorial. And then on bottom I have 2 factorial, that's 2 times 1. And then I have times 18 factorial. Now I could write 18 all the way to 1 and 18 all the way to 1 and cancel each of those out one by one, or I could just cancel that out. And then 20 times 19 over 2 times 1, well, the 2 and the 20 can reduce, and 10 times 19 is 190. So that's how we would evaluate factorials. Now this next part at the bottom of the page always looks a little bit intimidating to students, but it's really just a new notation. It's not, the math that you're doing is not very hard. This is called summation notation, and it's a way of writing the sum or the addition of several numbers together in a shortened way. So this symbol here means we are adding up a bunch of numbers from this term, the first term, to the nth term. This is called the lower limit and the upper limit, and this is the equation that defines the pattern here. So again, it's easier with this topic if we actually look at an example, and so that's what we're going to do on the next page here. Here we have an example with summation notation where we are wanting to find the sum of the first 5 terms. So from term 1 to term 5 following this equation here. So the first term, plugging in 1 cubed is 1. And then plugging in 2 cubed is 8. And plugging in 3 cubed is 27. And then 4, plugging in 4 cubed is 64. And then plugging in 5 cubed is 125. And if I add up 1 plus 8 plus 27 plus 64 plus 125, that equals 225. And that's all summation notation is showing us, is what we need to add up. Now this next example here is going the opposite direction. It's given us a pattern and it wants us to write this in summation notation. So we know we're going to have this symbol. This is the first term to the, we have 1 to the 4th power, 2 to the 4th power, 3 to the 4th power, and by that pattern, 4 to the 4th, 5 to the 4th, 6, the 12th term. So I equals 1 all the way to 12. And then the equation we see here, the thing that's changing is the base. So we have I, whatever our base is, to the, everything is to the 4th power. So that would be writing it in summation notation. The next one, the pattern's a little bit harder to see, but you can still see it here. And it doesn't show it, but 9 to the 1st power here, then 9 to the 2nd, 9 to the 3rd, all the way to the nth power. So we have the first term to the nth term. And it's not just the exponent we see changing, the top number is changing too. 1 first power, 2 second power, 3 third power, n nth power. So we have a couple of things for our formula here. We're going to have I on top and 9 to the ith power. Okay, so that would be writing our summation notation here. Now, there's 2 types of sequences and series that we're going to be looking at, and the first one is called arithmetic sequences and series. And this is the type of pattern where we are adding or subtracting the same amount from one term to the next. So if you see a couple of patterns here, we have 142, and then 146, and then 150, 154, and the difference is that we're adding 4 to get each next number. The next would be 158, and the 162, and so on. And what that difference here is called is the common difference. It was adding 4 each time. We can also decrease. So going from 8 to 3 to -2 to -7, we are subtracting each time. And so the common difference would be -5. It's decreasing each time. And we can find any term in this sequence by using the general form of an arithmetic sequence. And so we can write an equation for the pattern using the first term, n, and then the common difference. So let's see that in an example here. It says find the 8th term of the arithmetic sequence whose first term is 4 and common difference is 8. So before I write the 8th term, if I wanted to, I could find the general form, a sub n, and that would be the first term. So the first term is 4. And then I don't know what term we're talking about, the nth term, minus 1. And then d is -7. So the general form here is 4 plus, and then -7 times n is -7. Let me go ahead and get rid of this plus sign here. Minus 7, n. And then -7 times -1 is plus 7. So a sub n is equal to -7n, and then 7 plus 4 is 11. So now that I have this general formula, I can find whatever term I want. If I want to find the 8th term, then I just plug in 8. And that gives me -45. If I wanted to find the 100th term, I could plug in 100. Okay. Now, if we want to add up a bunch of terms in an arithmetic sequence, this is the formula that we're going to use. This is the sum formula. And notice here, instead of having it be a sub n, now it says s sub n, representing that we are adding up a bunch of terms. So here it says find the sum of the first 100 terms of this sequence here. Well, from one term to the next, I can see we are adding 2 each time. So my common difference is +2. And I know that my first term is 1, but I don't know my last term. But I can find it because I can write an equation for it. So I want to find the sum of the first 100 terms. I don't know n, the number of terms I know n, the number of terms I'm adding up. That's 100 terms. And I know the first term is 1, but I don't know the 100th term. I don't know a sub n, a sub 100. But I can find it by that formula that we had on the previous page. A1, 1, plus n minus 1. Well, n is 100 minus 1 times our common difference, which is 2. So a sub 100 is 100 minus 1 is 99. 99 times 2 is 198. 198 plus 1 is 199. So 1 plus 199 is 200. 200, and then 100 divided by 2 is 50. 50 times 200 is equal to 10,000. So that's the sum of the first 100 terms of this sequence. Now we can do this if we're given it in summation notation as well, from the first term to the 25th term. So we're adding up 25 terms, and this is the equation we have. Well, I'm going to need a 1, and I'm going to need a 25, the 25th term. And we know that the number of terms we're adding up is 25. So s sub 25 would be 25 over 2. And I need to find a1 and a25. So if I plug in 1, 1 times 5 is 5, minus 9 is -4. If I plug in 25, 5 times 25 is 125. 125 minus 9 is 116. So -4 plus 116 is 112. 112 divided by 2 is 56. 56 times 25 is 1,400. And that's the sum of the first 25 terms. Now the other type of formula we can look at is called a geometric sequence or series, and this is where we are not adding the same amount each time, but we're multiplying by the same number each time. So for example here, I have 4, 8, 16, 32, and notice the difference is not the same. 4 to 8 is 4, but 8 to 16 is 8, 16 to 32 is 16. So it's not the same difference each time, but 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, times 2 is 64. So you're multiplying by 2 each time. So we have what's called the common ratio. The numbers can also get smaller. If you're multiplying by a fraction or a number less than 1, then your numbers are going to get smaller. They can also alternate signs if you're multiplying by a negative. And the way you can find the common ratio is by putting the second term over the first term. So here I have negative 3 over 9, negative 3 over 9. So my common ratio is negative 1/3. And you can find the general term of a geometric sequence by using this formula here, a1, your common ratio to the power of n minus 1. So in this example, again, it's asking us to find the 8th term in the sequence, whose first term is negative 4, and common ratio is negative 2. So I could find the general form, a sub n. The first term is negative 4. My common ratio is negative 2 to the n minus 1 power. That's that formula right there. So then finding the 8th term would be negative 4, negative 2 to the 8 minus 1 power. And that would be 512. Again, you can just type that in your calculator. Okay. All right. So we can also find the sum for a geometric sequence using this formula here. And so if I wanted to find the sum of a certain number of terms, s sub n, I would use a1, 1 minus r to the nth power over 1 minus r. And we can go ahead and do a couple examples like that. So here we want to find the sum of the first 8 terms of the geometric sequence, 81, 27, 9. If I want to find the common ratio, 27 over 81 simplifies to 1/3. That's my common ratio. So I have my common ratio, and my first term is 81, and I want to find the first 8 terms. So s sub 8, sum of the first 8 terms, would be 81, the first term, times 1 minus, and my common ratio is 1/3, to the nth power, which is 8, over 1 minus, and our common ratio, which is 1/3. Now this is a lot to kind of simplify here, and you can do some of these calculations in your calculator, but when we evaluate this, we're going to end up with 3280 over 27. Okay. All right, and then the next one, we can do this with summation notation as well. So we do want to find our first term, so a1. Plugging in a 1, 2 to the first power is 2 times 6 is 12. We don't need the last term in the geometric formula. We just need the first one. So the sum of 1 to 10, so the first 10 terms. And then we would have 12. And our common ratio is the base of your exponent. This is our r value here. So I have 1 minus 2 to the 10th power over 1 minus 2, and here that gives me this 1 minus 2 is going to be negative 1, so I'm just going to rewrite this as dividing by negative 1. That's the same thing as negative 12 out front, and then we have 1 minus 10, 24, that's 2 to the 10th power, and then that gives me 12,276. Just 12 times that. All right. Now, one thing that is different about geometric sequences is that if we have a geometric sequence that's infinite, meaning it goes on forever and ever, we can actually still find the sum sometimes. So what we would have for our infinite geometric sequence, meaning a sum that goes on forever and ever, there's no last term, there's infinitely many terms, we can still calculate the sum of it as long as the r value is less than 1. So the absolute value of the r value needs to be between negative 1 and 1. If it's greater than 1, then that means there is no sum, or meaning we can't find the value of the sum. So here in this first example, it says find the sum of the infinite geometric series. We have negative 3, 1, negative 1/3, 9, 1/9. And so finding my common ratio, 1 over negative 3 is negative 1/3. And that is the absolute value of that is less than 1, so that means there is a sum. And then we can go ahead and use the formula above to find it. So we're using this formula right here. Now notice it doesn't say S sub n because there's not a certain number of terms we're adding up. It's infinitely many terms that we're adding up. A1 is -3, and 1 minus my common ratio, -1/3. Well, to simplify this, we have -3 over, and then in order to simplify the bottom here, I'm going to rewrite 1 as 3 over 3, and a negative times a negative is a positive. So -3 over 1 plus, or 3 plus 1 is 4/3. And when we divide fractions, that becomes -3 times, and then the reciprocal, 3 over 4. And you can rewrite -3 as -3 over 1 if you want, and that becomes -9/4. Okay. All right, and the last one says express 0.0 or 0.9 with a bar over it as a fraction in lowest terms. Now, 0.9 with a bar over it, that's 0.99999 and goes on forever and ever. Now, the way you could break that down, that's the same thing as 0.9 plus 0.09 plus 0.009 plus 0.0009 plus, and so on. And so that means if we were writing this as a sequence, that would be 0.9 plus 0.09 plus 0.009, so on. So finding the common ratio would be 0.09 over 0.9. Well, 0.09 is the same thing as 9 over 100, and 0.9 is the same thing as 9 over 10, and that's 9 over 100 times 10 over 9. The 9's cancel, 10 and 100 reduce, and that's 1/10. So that's my R value. Now to find the sum, that would be the first term, which was 0.9, over 1 minus 1/10. Well, remember that 0.9 is the same thing as 9 over 10. And on bottom, 1 minus 1/10 is 9/10. And anything over itself is equal to 1. So what we're saying then is that if we were to take this 0.9 with a bar over it and take that to infinity, add all of those numbers up, it would be equivalent to 1. Okay. So that's going to be the end of us looking at sequences and series. What we're going to look at next is some basic, very basic probability and principles of counting. So here we're going to be looking at what's called the fundamental counting principle. And this is how we calculate some basic either probabilities or counting properties. So here, looking at this first example, it says if you have 6 pairs of jeans, 10 shirts, 4 pairs of shoes, how many outfits can you make? Okay, so the fundamental counting principle is the number of ways that a series of successive things can occur if found by multiplying the number of ways each thing can occur. So let's just think about our 6 pairs of jeans first. Let's just say we're starting with jeans. So let's just say our first pair of jeans, our second pair of jeans, our third pair of jeans, our fourth pair of jeans, fifth pair of jeans, and our sixth pair of jeans. And then I say, okay, well, this pair of jeans could go with shirt 1, shirt 2, shirt 3, shirt 4, shirt 5, shirt 6, shirt 7, shirt 8, 9, and 10. And I can do that for each pair of jeans here. So 10 lines, 10 lines, 10 lines, 10 lines, 10 lines. And then with each of those shirts, I could say, okay, well, from there, there's 4 pairs of shoes, 4 pairs of shoes, 4 pairs of shoes. And so each one of those could then multiply out. And if we drew out all of these lines and I used a whole sheet of paper to draw them all out, that's going to be equivalent to the 6 pairs of jeans times the 10 different shirts times the 4 different pairs of shoes. Well, That's going to be 240 different outfits you can make with 6 pairs of jeans, 10 shirts, and 4 pairs of shoes. Okay. So that's the fundamental counting principle. And then the next thing we're going to look at are permutations and combinations. And hopefully in a previous math class you've been exposed to this, or you've seen this a little bit before. But permutations and combinations are looking at how many different ways you can arrange things. Permutations, the big difference between permutations and combinations is that here with permutations, the order of the items matters, whereas for combinations, the order doesn't matter. So for example, with a permutation, if I was going to have a race with 10 people, and I was going to see who was the fastest, and I was going to give medals for first place, second place, and third place, giving gold, silver, and bronze medals. It matters whether you come in first or whether you come in second or you come in third. You're not getting the same thing. The order matters there. But if I was saying, okay, I have 10 people who are racing, and the first 3 people to pass the finish line get a $10 gift card. Well, then it doesn't matter. It doesn't matter whether you come in first, second, or third. You get the same thing. So those are the examples of permutations and combinations. Permutations, the order matters. Combinations, the order does not matter. And these are the formulas for each of those. So permutations, if you have, in the example I just gave, that would be, if you have 10 people who are racing, that would be 10 factorial over 10 minus, and then I was choosing 3 to come in first, second, and third place, 3. And then you calculate that. For combinations, the example I just gave where I said, okay, we've got 10 people racing and the first 3 winners to cross the finish line get a $10 gift card, then that would be 10 factorial over 10 minus 3 factorial, and then also times 3 factorial. So this is going to be a smaller number than this. It's also possible that they're equal in some scenarios. So we're going to look at some examples here and determine first if they're combinations or permutations, and then we want to explain why, and then we're going to also calculate them. So the first one says 50 people purchase raffle tickets. 3 winning tickets are selected at random. If each prize is $500, and how many different ways can the prizes be awarded? So there's 50 people and purchasing raffle tickets. There will be 3 winners, but each of those 3 winners, they each get the same thing. They each get $500. So this would be a combination because what they're getting is not different. If you come in first, second, or third, of those 3 winners, you're getting the same thing no matter what. So we're going to use a combination that's using NCR equals n factorial over n minus r factorial and then r factorial. And in this case, that would be 50 people choosing 3. Oops, not a C here. 3. So that would be 50 factorial over 50 minus 3 factorial, and then 3 factorial. So 50 factorial, 50 times 49 times 48 times 47 factorial. And then 50 minus 3 is 47. And then 3 is 3 times 2 times 1. So the 47 factorials will cancel. 3 times 2 is 6, and 48 divided by 6 is 8. So 50 times 49 times 8 is going to give us 19,600. So there's that many ways that can occur. Now let's look at the next example, and it says 50 people purchase raffle tickets. 3 winning tickets are selected at random. If first prize is $1,000, second is $500, and third is $100, and how many different ways can the prizes be awarded? Well, in this case, you really care whether you're the first winner, second winner, or third winner, because there's different prizes for each of those. So this would be a permutation, because you're not getting the same thing in each of those places. So we're going to use the formula for a permutation, and that's n factorial over n minus r factorial. And that's 50 factorial over 50 minus 3 factorial. So 50 times 49 times 48 times 47 factorial over 50 minus 3 is 47 factorial. Those cancel. There's no reducing that 48 in this case, so that's going to be 50 times 49 times 48, and that gives us 117,600. So obviously many more ways that that can occur. And that is the very end of Part 4 and the end of Unit 3 and the end of the course.